Okay, everyone, so time to begin here. And we are on page 125, this chapter 25 summary. So what we're going to do today, this being our last class before the exam, we're just going to spend maybe 15 minutes finishing up the new material. And then we're going to just jump right in and do the yellow practice exam in your notes together. So, because this is our last class before the exam. So then if you have, our exam is Monday night this time, and you can come to office hours today, 4 to 6, Friday, 4 to 6, and we can do Monday office hours 2 to 4. Because then the conflict exam starts at 4:30. Does that sound good? Yeah.
Is chapter 27 also going to be covered in the midterm?
Chapter 27, is that going to be covered? Let's just look and make sure. We'll see. It's everything up until the yellow pages here. So yeah, it is. That's what we're going to do today. We've already done it, so it's super easy. We've already done it for regression. So let's just jump right in. And here's our summary. And I think we went over this last time, but if we haven't, there's basically two ways to do. This is the summary for testing, doing these post hoc multiple comparisons for ANOVA. You have multiple groups. The null is that their means are all the same, right? The example that we're looking at is that the 5 ethnic groups. The null is that even though we saw differences between how whites, blacks, Hispanics, Asians, etc., viewed gay marriage, their opinions on gay marriage, this is the last example we were doing, we saw the average rating for how strongly they were opposed to gay marriage varied, right, among the groups. The null is that those variations are those differences are small and just due to chance variation. And the alternative for the overall test is no, at least one of them is different. So then we looked at individual pairwise differences and there's to see which one is significant, right? And there's 2 ways to do this. One was they're basically depending on when we state our hypothesis. If we single out which group mean will differ before looking at the data, well then we only have one difference and we don't have to adjust for multiple differences. We've singled out this one is different, so we don't have to make any Bonferroni correction. But if we single out which group means will differ after looking at the data, well, think about it. If you had 100 pairwise differences and you picked the 5 biggest difference, well, just by the luck of the draw, those are going to be statistically significant by definition at 5% level. So you have to make some adjustment if you cherry pick which after looking at the data, which differences are going to be significant. So you have to adjust it by the Bonferroni correction, which is the number of pairwise differences you have, which is if you had 100 groups, you'd have 100 times 99 divided by 2 pairwise differences. It's G, the number of groups, times G minus 1 over 2. Okay? Questions on that? All right, so now the next thing we have to do is look at these assumptions, chapter 26, and I'm going to, these are exactly the same as what we did for regression. So there's really, it's important to note that we have some underlying assumptions that need to be met to make sure these ANOVA results are trustworthy. To use this F test, T test, Z test, chi-square, they all depend on certain assumptions. And they're the same ones as for regression that we already went over because as we saw, this is a specific case of regression, right? Predicting some quantitative variable based on group membership. So they have to be independent. The errors have to be independent. We have to have random sampling. That means they have to the errors around our model have to be normally distributed with equal variance, and that's basically our assumptions here. And we're going to examine those later after exam 2 because we're going to look at plots of errors and do transformations of the variables to see how to meet these assumptions. So we're going to check residual plots and do different things after. That's after exam 2. All right, so for now, let's just forget about that now and concentrate on what's going to be on the exam, which is chapter 27 here too. Okay. So now we're on page 129. Okay, so we're going to do this randomization test. And this is the same test that we did back in chapter 22. For linear regression, now we're doing it for ANOVA. Same as in chapter 22. The first thing you might say is, wait a sec, we often don't even have a random sample. Certainly in this case that we're looking at, where you have the 858 students from a former Stat 100 class who on survey data gave on a scale of 1 to 10, rated how opposed they were to gay marriage, 10 being the most opposed, 0 being the least. And we saw these differences, but they weren't a random sample. So there's two ways we deal with this. We didn't randomly sample them from some bigger population of Stat 100 students. We could imagine we do that, and that's what we usually do. So technically, we can't do a significance test without some kind of random sampling, because it's based on, like all significance tests, those p-values are based on sampling distributions, which involve random draws, right? That's what they are. So if you can't model it with random draws, you really shouldn't be doing a significance test. But people do them all the time, so you have to think about if it makes, sometimes they do them all the time and they're wrong, because they should be thinking about it, and it can't be translated into a random sample. In this case, I think it can be, so we have to think about how we would do that, okay? So here's the thought process. So you picture one of these two scenarios and see if either of them makes sense, and then you can go ahead and do the significance test. So what we've been doing so far using ANOVA, using the F test, right, and with all our what's called parametric statistics, the F, the T, the chi-square, and the z, we imagine a large population of all possible Stat 100 students from which these 858 students were randomly drawn. The null is that there's no real difference between the mean group attitudes in that imaginary population, this idealized population. We compare an F or a chi-square statistic and look at its sampling distribution under the null. That's what we do. That's what we've been doing when we do these ANOVA. So that's what, and set up the ANOVA table, etc., or compute the, all right? Now, there's another way to do it, and that's by imagining a randomized experiment. The null says that knowing which ethnic group someone is in tells you nothing about the person's attitude towards gay marriage. There's no, squared is equal to 0. R is equal to correlation, tells you nothing, right? That our best estimate would just be the overall mean of everybody. If this were true, if the null was true, I could randomly assign the ratings among the 5 groups, and it wouldn't be surprising to get the differences we observed in our sample just by random luck. We can simulate doing this experiment on the computer just as we did for regression. So that's what we're going to do, and this is the randomization test. All right, randomization test. All right, so ANOVA assumes this first imaginary scenario and requires those assumptions to be met that we just talked about in order for it to be valid. All right, and the randomization test enacts this scenario and has the advantage of being distribution free. It doesn't rely on all those assumptions. All right, so that's what we're going to be doing. All right, so let's just get right to it so we can get to the practice test right away. I think you'll understand, you understood it very well when we did it with regression. It's the same thing. So let's write that down. It's the same idea as before, as in chapter 22. All right, so our data set is 858 Stat 100 students' responses on two variables. One's categorical, their ethnic group, and the other is quantitative. Their rating from 0 to 10, where 0 means strongly in favor of gay marriage and 10 means strongly opposed. All right, here's our 5 groups right here. And the question is, are the differences in the average ratings between the ethnic groups real, meaning are they due to some particular cause, or are they just due to the luck of the draw? Is this just random variation? You know, so let's imagine, a way we can imagine that is to randomly assign the 858 ratings, randomly divide them into these 5 groups. According, put 448 in the white group, 84 in the black group, etc., and do that and get a statistic, the R statistic, saying the correlation between these predicted ratings and the actual. Okay, let's look at this. We saw that the correlation between the 858 predicted ratings made based on ethnic group and actual ratings is, there's a correlation there, and it was strong enough because the sample size is big. It doesn't look like it's that big, it's about 0.2. That's the correlation between what we'd predict based on their, so if you're white, I'd predict your rating to be 2.26. If you're black, 3.643, right? I just predict that. And that does better than just giving the overall average for everyone. That's what we're saying. So we did an F test, and it showed that was very significant. So there's another way we can do it. We can do it by just seeing how likely it is to get that big. We can compute a p-value by just saying, okay, if we randomly took all those ratings from 0 to 10, all 858 of them, shook them up, put them in a box, so we'd have a box full of numbered tickets, right? And I draw out 448 of them, just at random. Take their average, and I'll get a different average than that. I'll draw out the next 84, and take their average, just random 84, and there'll be a different one. It'll be a different average, and a different average. They'll be the same sample size, different averages. And then we'll see, they're not going to be exactly the same, right? Just by the luck of the draw. And we're going to compute an R for each one of those. And then we'll do the sampling distributions of the R's, just as we did before. Okay? So let's test it. So the attitudes so here's our null towards gay marriage are unrelated to ethnicity. Knowing somebody's ethnicity tells you nothing about their attitude. And the alternative is the attitudes are related to ethnicity. That it does give you some predictive power. So here's how it works. If there really were no relationship between attitudes toward gay marriage and ethnicity, then we could expect to see any of the 858 ratings randomly associated with any of the 5 ethnic groups. In other words, we could scramble up the ratings and randomly assign them to each of the 5 ethnic groups without replacement. That's what I said. The first 48 ratings could be assigned to the white group, the next 84 to the black, etc. And then we'd compute for each one of those an R. And the p-value would be the chance we'd see an R is extreme or more extreme than our sample R if we enacted the randomizations over and over and over again. Let's just do that so you can see what I'm talking about. Okay, so it's the empirical. We're going to get a distribution that's the empirical sampling of R under the null. And this is after how many randomizations? Here's histograms of 1,000, our sample is marked by this vertical line. So there's our sample. Its p-value is computed to be 0% since none of our randomizations, none of the randomizations had an R that big. Okay, so that's what we're doing. So let's look. And here we go. So here's our data. And we'll just click on this re-randomization. So right now we have a p-value of 0 doing the f-test. And we got a tiny, tiny p-value. Let's see what re-randomization gives us. So we'll do it. So after 1,000 re-randomizations, what do we have? We have a p-value of 0 after 1,000. All right, so let's look and do more. You'll see if this goes up. I don't think it will. We're pretty far out there. Let's see if it does. So we'll do more re-randomization, 2,000, see if we get anything. Any of our R's is as extreme or more is as big as the one we got in our sample, which is this. I don't think so. It's going to get to be a smooth curve. Let's check it out. No, we're not even, I can see they're getting close. You can see a tiny bit. It might not be showing up on here, though. It might not be, I think you need 4 significance digits to show up on here. Let's see, we'll do some more. I mean, if you do this long enough, of course you're going to get some. It just might not, I can see there's this faint line out here. But the chance is so tiny, and that's the p-value. Okay, so that's the idea. And so this right here is our observed R. And we see that the p is equal to 0%. And that's, sorry, go back to the document camera. Okay, and that's pretty much it. It's the same as we did before, so any questions? Okay. And here's our summary. And let's see what we need to think about here. This is a nice summary, so you can read this on your own. And you should read all the summaries, as they're good review for the exam. All right, so now let's just start right here with the exam. So we're on page 134 in your notebook. Okay, so this first question is very standard. What I'm going to try to do is not just write what's on here, what's in the key, but give you some maybe tips on how to think about it and how to approach the problems or easier things to do. All right, so let's read this. And we're trying to fit this simple linear regression model for the whole simple. That just means 1x predicting 1y. So we don't have to do a chi-square and f. I just want to show you how they're related. Okay, and we draw a random sample. These are what we need here. A random sample of n equals 47 from the population, and we get a sample correlation of r equals 2. All right, so now we're going to compute these 4 test statistics. And we're testing the null that the slope is equal to 0, which is the same as testing that r in the population equals 0. All right, so we're going to let's round the answers here. All right, so the first thing here is this is just to help you so you don't make careless mistakes. I say r squared is equal to 0.2 squared, which is that. So this is 0.96. Now I think the simplest way to do this is actually to start with the chi-squared and the f, because they're easier to compute since they don't involve square roots. Okay, I assume all these people who are leaving just don't want to see it now because they want to work it out on their own. I think for this one, I think either way would be fine. To stay here, or I recommended leaving for the first exam, but I think for this exam, either way is fine. I should have said that at the beginning. Okay, certainly if you have questions, you might have questions, you should stay. but I don't think it's going to hurt you to stay on this. I think it might be helpful. All right, so now, so the chi-squared and the f here. All right, so the chi-squared, as you remember, how are you going to remember this? Okay, both of them have this core r squared over 1 minus r squared. And you already have your r squared and 1 minus r squared, right? And this right here is always just multiplied by n. That's the easiest one to figure out. All right, let's do this first then. It's the easiest one. So what are we going to have? We'll have r squared 0.04 divided by 0.96 divided by n, and we have n right there, which is times 47. So that is really easy, and we get 1.958. Now, the z is just the square root of that. We're in simple regression, so we can do this. If we weren't in simple regression, it wouldn't be appropriate to do a z. But we are, but it's either plus or minus the square root of the chi-squared, right? That's what it is. It's r over the square root of 1 minus r squared times the square root of n. Now, how do you know if it's plus or minus? Well, it's going to correspond right here, this plus or minus, to whether this r is plus or minus, right? In this case, it's going to be plus, because r is plus. All right, so we'll just take the square root of that, and we're done here. And I did that, and I got 1.399. Okay, so that's that. Now let's move on to the f and do the same thing. So the f has that core part of r squared times over 1 minus r squared. But now, instead of n, it's n minus the number of parameters. And you have to divide by p minus 1. Now in this case, you want to know how many parameters, how many numbers. Well, that is given to you right here, how many betas in this model. So the number of parameters for simple regression is equal to 2. So that's what we're doing here. So we just say, okay, we have the same thing, 0.04 over 0.96. Now, instead of 47, it's 47 minus 2, 45, and here it's 2 minus 1. So that's really what you're doing, even though I didn't put that in before. You just have to remember one formula. It's always that. It's just here. With simple regression, 2 minus 1 is 1, not down there. All right, so we do that, and we get 1.875. Then t is just plus or minus the square root of the f. So we got the square root of 1.875. And it's positive, of course, again, because we have a positive r. If that was a negative 0.2, we'd have to put negative in front of it. And I got 1.369. All right, so now we've got that. Now we're going to compute the p-values for each statistic, assuming this, that the z and t are one-sided. If they were two-sided, then our p-values would be the same for the z and the chi-squared, but they're one-sided, so we have to be a little careful. Remember, the chi-squared in f is always non-directional, always two-sided. It's non-directional. Even though you're only looking at the right side of the curve, it's non-directional because it can only be positive. Yeah? Why the what? P? Oh, the error. The P, this error, P is 2. Any questions on that? Why it's 2? It's the number of parameters in your model. This error is not a parameter. That's just, it's because I didn't do this predicted. I could say predicted y. The error is not a parameter. You're not estimating a beta for the error. You can write it that way, as the y's are equal to something plus some error, or your predicted y's. Those are just the ones on the regression line. These are the actual y's that are above the regression. Does that make sense? So yeah, good catch now, because maybe that's why a lot of people get it wrong in the exam. Okay? So it's just the number of betas. Another way, okay. So now, here we are here, and so what do we want to do? Okay, so we want to get these p-values. So you're looking here at 1.399, and you have to place it on this curve. Where do you put one? Boy, that doesn't look right. I'm sorry. Let's just see why that's not. All right, so you want to get the p-value. You have to use the normal table to get this. So what we want to do is just look at how extreme that is. We know zero's in the middle, and we just want, so we have 1.39, this is 1, 2, so it's somewhere in between here. So between 1.399 and negative 1.399, we're going to have to look at the normal table to get that area, because this is what we want. Because the alternative is directional, that we're going to see a difference. The alternative is that it's going to be greater than 0. So we just want that tail. So I looked up 1.4 in the back of the book and got 83.85. All right. And now I'm just going, the p-value would just be 100 minus 100% minus 83.85 divided by 2. And I got 8.075%. All right? Now, you have to be careful, because I'm not always going to write it like that. What if the alternative was not equal to 0? What if there was the same, the two-sided? Then what would you have to do? Then you'd have to include that as well, obviously, both tails for the two-sided, and then you would get twice that. Then p would be equal to twice that, which is what, 16.15%. Okay, does everybody understand that? Questions on that? All right, so that's just looking at the table. In case you're rusty, you go to the normal table, which, it's right at the back of your exam here. Let's just use it. And we looked up 1.399, which is closest to 1.4, and that's where I got it. 83.85 in the middle. Any questions on that? Okay, so now we're on to our next one. And now the chi-squared. Now the chi-squared is going to give you the same as a two-sided z here, so you can just write 16.15. Any questions on that? Because it can't give you a negative, it can only give you the positive. How many degrees of freedom? Well, the degrees of freedom are p minus 1. The same as here. Same as the numerator. That goes with the numerator of the f. And that is equal to 2 minus 1. So that's 1 degree of freedom. All right. So you could look that up on the table, except I don't think the table gives you an exact p-value. It's just going to give you null cutoffs. But you could look to see if you're about right. So you'd go to 1 degree of freedom, if you wanted to, on the table which will be provided. 1 degree of freedom, and we got a p of 16. We got a chi-square of what? Excuse me. A chi-square of 1.958. So you'd have to look up 1.958, which is right in between here. So what you just know it was between 10 and 30. And 16 agrees with that. Does that make sense? Yes.
Twice as the p-value in z test. What is the p-value of chi-square twice as much as the p-value?
Why is the p-value? Because we're measuring the same thing. It's just, in this case, it's just a z squared. So if you're squaring, it's just a z squared. So we're taking this, so it's going to be the same thing. It's just, that's what a chi-squared is. It's the sum of z squared. So with just 1, it's just squaring the z statistic. And if you square it, you could get negative or you can't get, what's your question? The p-value.
P-value
It's the same curve. Okay, sorry. Chi squared is equal to z squared. When you just have 1 degree of freedom, you square the z's. You square all the z's, like if you squared all this side, right? You squared all that, they would all turn positive, right? And anything between 0 and 1 would go up, would become smaller. So you would get a curve that looks like, I'll just do it quickly. Okay, so here you have the normal, which is z, and you're just talking about z-scores. And here you have the chi-squared with 1 degree of freedom. And I'm just saying it's this squared. So -1, 1, 2, -2, etc. So this is equal to z squared. So they have to be positive, right? And so everything between 1 and -1, when you square it, 1 will stay at 1, -1 will stay at 1, but anything in here is going to get smaller. For example, a half will become a quarter, right? So it's going to pile up like that. And then anything out here, like 2 squared is 4, so it's going to look like that. Now, we had a statistic as a z-score of 1.4, like around here. We squared it. We got almost 2, a little bit less than 2, right? And that's just, so this area is just going to be the same as that area and that area, because these two together are going to go over here. Does that make sense? The negatives and the positives are going to go over there. All right, that's the idea. Okay, so now, where are we? So now what are we going to do now? For the t, we have 1.369. All right, now we have to choose the closest one. How are you going to know? Well, I didn't provide you with a t-table that went up high enough, so you can't use that. So what do you want to do? You know what? You know that the p-value for the t, this is what you should know. How does it compare to that? P-value for t compared to p-value for z. Is it bigger or smaller? It's always bigger. Why? So this is the only one that's bigger. Why is it bigger? Why? Because the t distribution has fatter tails. And the p value is how much area is in the tail beyond your statistic. Okay, so it has to be that one. These two are smaller than what we got there. How many degrees of freedom? Now, the degrees of freedom is the same as n minus p. The same as for the denominator in f. So that is equal to 47 minus 2, which is 45. Okay, now choose the closest one. Well, since this was one-tailed, we're going to have to double it, because this is for the two-sided test. And how many degrees of so it's 2 times 9, right? Because that was one-sided, and this always is two-sided, always is non-directional. It's not, you're not taking, it can only be positive, so the negatives and these two tails in a symmetrical distribution both get lumped together on the right side. All right, in these distributions. And how many degrees of freedom in the numerator? Now don't get confused by this. Remember, this we simplified, but the numerator has the smaller, has just, it's going to be 2. In this case, this is p minus 1, and this is n minus p. So that's 1 and 45. Okay, any questions on any of that? Next one. Which of the following 4 quantities do you have enough information to calculate? If you have enough, do it. can you calculate SST, the spread of the, no, because you need the standard deviations of the y's. You need to figure that out, and we don't have enough information to figure that out, so you can't do that. Remember, SST is equal to n times the SDY squared. And we don't have that one, so we can't do that one. How about SSM? What is that? Remember, that's the proportion. SSM is equal to what? SSM is equal to the proportion, is equal to R squared. That's the proportion that's times SS2. It's the proportion, that's the R squared is the proportion of the total variation of the y's that's due to the model. And since we don't have that, we can't do this one. All right, but we can do this ratio just because of this relationship. Look, SSM over SST is R squared, see? That's the proportion of, right? So we can do that one, and that is equal to just 0.04. That's your answer there. How about this one? We can do this one too, because SSM is R squared times SST. And SSE is, that's, remember the sum of squares model is the proportion of the total variation of the y's that's due to the model. And SSE is the proportion of the total variation of the y's that's left in the errors. So we can do that. So we have that. So what is the answer? The answer would be 0.04 over 0.96. Okay, so now, so these are just, this is a conceptual question here, or just you compute, well, sort of conceptual. You compute an F and chi-square test to test that all the betas in this model that has these 4 slopes, 5 parameters, n is equal to 200, and p is equal to 5. How do the chi-square and the F test compare? It will help if you look at these curves. I drew the curves down here to look at them. Okay, so here's the 2 curves. Which is which? Remember, the F is centered at 1 always, or very close to 1. So the F has a mean of about 1. Look, compared to this one, where the mean is much higher. And the chi-squared, this is the chi-squared, and its mean is always equal to its degrees of freedom, which is p minus 1, in this case, 4. See? Degrees of freedom. This is p minus 1, 4. So the chi-square stat, you can just see it's the middle of it is 4 times greater, is the degrees of freedom greater. So that's 4. All right, and this is A. Any questions on that? So if you look at the, it's always going to, it's about 4 times big. It's about that much bigger. It's going to be slightly different, with the one will be multiplied by 200, the other will be multiplied by 195, but this is the big difference. Okay, so let's move on. So now these are sort of the basic calculations involved in sum of squares model, sum of squares error, and sum of squares total. And here you just have 3 points for regressions, so they're really easy to do. So we might as well see how to do these and make sure you understand how to do them. So what do we have here? We have these 3 points, 110, 3.2, and 8.21. And we fit it with this regression equation, right? So we made predictions. Here's the okay, so we're going to compute. We want to compute SSM and SSE, and you're given SST. Okay, and you're also given that the average of the 3 points the 3 y's is equal to 11. I didn't have to give that to you. You could say 21 plus 12 divided by 3, and you'd get 11. All right, so now what do we want to do? The sum of squares model, you should know, is the sum of from I is equal to 1 to n. In this case, n is 3. So we just have 3 points. Okay, of your predicted y minus the overall average, what the model predicts squared. All right, so we can do this. We have to get, so we have this, so it's going to be 3 points. Each one's going to be minus 11 squared. Minus 11. But we have to get these 3 points from here. These are the points that are on the line. So when you plug in a 1 for x here, like right here, what's that point? This is what we're trying to figure out. We plug in a 3, what's that point? And what's that point? That's what we're doing. All right? So when you plug a 1 in, 2 plus 3 is 5. So that's the point 1, 5. Right? We have the actual point 110. This is the actual point 3, 2. And this is the actual point 821. We're just looking at the y values, though. All right, and now, so what are we going to plug in here? This right here is our, I'll just put little hats on it so it'll be easier. These are our predicted, whoops. We haven't done that one yet. It's going to be 3. If you plug a 3 in there, you'll get a 9. So that's, I'll just say that's our predicted one. And if we plug an 8 in here, we get a 19. So that's our predicted one. All right, so we're just taking those 5, 9, and 19. And that's, and if you want to check your work, remember what the reason we're squaring these is why. The reason we're squaring these is if we didn't, what would they add up to? 0. So that's a good way to check your work. Say 5 minus 11 is negative 6, right? If we didn't square it, look, 9 minus 11 is negative 2, plus 19 minus 11 is 8 squared. Now, if we, inside the parentheses here, should add up to 0. And they do, 8 minus 8. That's why we have to square it. Otherwise, we'd always get 0. All right, so what do we get? We get 36 plus 4 plus 64, which is 104. So that's the sum of square model. Now you could be done right now because I gave you, you know they have to add up to this plus this has to add up to 182. So you could just say, figure it out right from there, but let me show you how to do this. So what would we do? We still have the 3 points. Now what is this? The sum of squares error. So that's each point, y sub I, minus the observed minus the predicted. All right, squared. So 10 minus 5 squared, plus the next one is 3 minus 9, plus 8 minus 19. Oh, here, I'm trying to do these. I should say those are the y's so I don't get confused. 10 minus 5, 2, see what I did wrong? I took the x, so it's important to 2 right here. That would be an easy mistake to make. We're just talking about y's, so maybe it's good to highlight them. So 2 minus 9, it's right here. Okay? And the last one's going to be what? 21 minus 19. And again, you could check inside here if you wanted to, just to make sure your arithmetic's right, that inside here, 5, that, plus negative 7, 2, plus what's this, 2, adds up to 0, and it does. And then we square them. So we get 25 plus 49 plus 4. And what does that equal to? That equals to 78. So now you want to check what? That 104 plus 78 equals 182. And you didn't have to go through that. You could have just done the subtraction. Once you found out 1, you didn't have to do both. But it's a good check. All right, any questions on that? Now, let's move on. Suppose A and B are 2 drugs designed to prolong life in patients with terminal cancer. The numbers in the table indicate the mean survival time in months for those who received A alone, B alone, neither, or both. Each table describes a different hypothetical study, and you want to fill in the 8 blanks in the tables. So they match their equations, 1, 8, and the 4 here in the equation, so it matches its table. All right, so let's do that. So this is very straightforward. So here, you're just plugging in when A and B are 0. Plug in as this is when you don't take either drug. You plug in, you get 0. And this right here says when B is 0, but A is 1, you get 10, and that's what this tells you. And then this is 6, because that's when A is 0 and B is 1. And then there's no interaction term, so this is just going to be 16. But you could just put a 1 in for both of them, and you get 16. 10 plus, right? So this adds an interaction term. It's all right, so again, you put 0 in for all of them, you get 0. When B is 0, this is 10. When A is 0, this coefficient is 6, right? That's 6. And now you don't get 16 here. You said when you put 1 in for both of them, you put a 1 here, and 1's for both of those. And you get 10 plus 6 plus 5. So that's 21. 5 more than you got here. All right, now let's do this one. This one's just going in the other direction. All right, so it says, okay, when you have here, when A and B are all 0, we actually still get something that has an intercept. So you get some benefit, 4 in this group. For some reason, it's a different group. All right, so that's 4. And now, what's it saying? Okay, so now, when B is 0, and what does A alone add? It adds 10. 4 plus 14 is 10. What does B alone add when you get rid of those two? B alone, without A, when A is 0, so you're just adding 6. So this is, all right. And so now what do you get? You get 4 plus 10 plus 6 is 20. If you didn't have an interaction term, but we want to make it match up to 17, so 20 what? I want to make it equal to 17, so I have to put minus 3 in there to make it equal to 17 when it's all ones. Okay, so let's go to our next problem. And so these are 2 scatter plots, and one's for males, this one's for males, and this one's for females, heart rate versus temperature. Okay? So they have different, and here's your equations. And what we want to do is translate it into a multiple regression by making it by adding gender. And since they have different slopes, we're going to have to add an interaction term too. So we want to combine these into a multiple regression. So of course, the way to might think about it is these are just x, y, but when we combine it, we have a third variable, and it's gender. So now we're not in 2D space, we're in 3D space. And it's a 0, 1 variable, and we have to say, okay, this is important. Males are equal to 0, and females are equal to 1. So think about it this way. If we were going to graph it, we'd have to have another axis coming out of here like this, and this would be our gender. When gender is equal to 0, we'd be down and we'd get exactly this. When gender is equal to 0. When gender is equal to 1, we go up to here, and then we'd lift this female and put it up there. And that would be our graph. We'd have this when it's 0, and when it's up here, we'd get that, as long as we have this interaction term. So that's how you should think about it. So we're going to start, since males are 0, we'll just put this right here and here, ignoring that. Okay, so let's do that. We certainly got that when males are 0. That's super easy. So we get negative 88 plus 1.6. Now, when we want to get this, when females, we want to get this when we put a 1 in here and a 1 in here. So now what we want is to get, instead of negative 88, we want negative 234. So how are we going to get that? Well, do you see negative 88 plus what gives you negative 234? It's just the difference between these two. So negative 88 plus what is going to give you that? That's what you want. So it's just going to be the difference between those two. Negative 234 minus negative 88, and you get negative 146. And just check those two. When you put a 1 in there, that gives you your intercept, right? And now what do you want to add to that to make 3.1? 1.6 plus what should I put in here? Because when you put a 1 in here, you'll get temperature. You'll just say 1.6 plus 1.5 equals 3.1. So this is just the difference between 3.1 and 1.6. So that's the idea. Any questions on that? All right. So now if you switch the code to males equal, which of the following would change? Would these change? No, that doesn't even have gender in it. So why would it matter? The scatter plots don't even have gender in it. You're not seeing this would change. So what would it change to? It would change to what? Just think about it. You'd have the heart rate equals, well now this is 0, so start with this one. This is 0, and now we're going to, we'll have an axis like this, and then when gender, this is the gender axis, 1, we'll get that equation. So we'll start with putting that in here, so we get negative 234 plus 3.1 times temperature. Okay? Now what are we going to add when gender is 1? That'll be when you have, now we have males. We want to change that to that, right? So it's just going to be the difference between them, but in the opposite direction. So instead of negative 146, it will be positive 146, right? It'll just be we're going in the other direction, that's all. We're subtracting the other way. And so when we add those two together, we get negative 88. And then for the interaction term, we want to change, that's gender times temperature, we want to change 3.1 to 1.6. So instead of adding 1.5, we'll subtract it. It's just the same difference. Okay, so that's the idea. And let's move on. All right, so this is a multiple regression example, and you're given that, what are you given? That 123 households, randomly selected husband-wife households, that's our N right here, in the city. You're predicting income, household income, from years of education for the wife and years of education for the husband. All right, so let's look at this. So we have this multiple regression equation and predicted income, and that is going to be what? We have basically an education, we have 2 X's and a Y, and that is the best. The above equation describes the best fit. It's not a line. We added a variable, so it's a plane. through all the points so as to minimize the sum of squared errors around their incomes, around the predicted incomes. We're trying to minimize that. All right? So that is around the incomes, the predicted incomes. I should put a little hat around it. Okay, so what does, I'm sorry, but this is very hard to see. Maybe it's because, okay, so what does the 4,000 slope mean? And the multiple, this right here. What does that mean? Well, it's a slope in front of the education of the husband. So it says, for each additional year that a husband is educated, the household income will increase by $4,000. That's what it would mean just in a simple regression. But remember, we're in multiple regression, so we have to control for the education of the wife. That means after we've put in this in the model, so for what additional information or explanation can this give us? So it means for controlling for it means for husbands who have the same, who are married to the same level of education for wife. So if you take two husbands that are both married to women who, let's say, have a 12th grade education, then for them, this is the difference, as long as they're controlling for the wife's education. This is how much their additional year will matter. So let's look at that. So you always have to think about that. With multiple regression, it's controls for all the other variables in the model. So for those husbands with what? Yeah, of the same educational level, each extra year of husband's education increases, whereas in the simple regression, it would just be regardless. It doesn't take into account. It doesn't control for. It says it's just an estimate of all husbands, no matter what their wives' educational level is. They'd increase by 4,000 if it looked like that in the simple. All right, calculate the predicted household income for a married couple who have only 10 years of education. So this is a prediction. This is an equation that makes a prediction for different educational levels. So I'm saying, well, if they're both 10, just predict. So you would just make the prediction equals negative 9,580 plus 10 times that, 25,000 plus 10 times that plus 40,000. And that gives you 65 minus that. So I got 55,420. Any questions on that? That's super easy. All right. Now, consider two couples. So two pairs, Adam and Alice and Billy and Baby. Okay, now the husband in the A group has 3 more, that sounds funny, Billy and Baby. I just wanted an easy way to remember what was going on. So couple A, the husband has 3 years more of education, right? And couple A, the wife has 8 more years of education. So how much more household income would A have than B? How much more? Well, for each extra year of, so how much more? We just have to think, okay, 3, he has 3 more years, the husband does, and the husband's increases by 4,000, right, husband. So it's 3 times 4,000 more just for having those. And then his wife has how many more? 8 more years. Oh, she's a lot. Baby is not very educated. So it's 8. That's why I called her Baby probably. That's 8 times 2,500. Okay, so that's it. That's the difference. You can just think of it if you plugged in Baby and Billy, and then you plug in the other ones, that would be the difference between them. And that's 32,000. So, any questions on that? All right, so we're moving just right along. This is pretty straightforward, and I think this will give you a good, these problems, this exam gives you, is a nice summary of what we've done. These problems are helpful in understanding what we've done. All right, so look at the correlation matrix for this. Remember the correlation matrix relating all 3 variables. Fill in the 4 missing blanks. Okay, let's fill those in first. So if you look at a correlation matrix, there's 1s across the diagonals, right? Because there's a correlation between there's a correlation of 1 between a variable and itself. Now the off diagonals, see, like these two, that's not the off diagonal. See, these two are the off diagonals. These two and these two. Let's fill those in. All right, so how can we fill this in? This is the correlation between the husband's education and the income. Well, wouldn't it be the same as between the husband's education and the income? And this one, the same way. Any questions on that? The tables for simple are correlations between 2 sets of variables. That's what that is. It has nothing to do with multiple. It's just if you look at them separately. All right. Now, look at the correlation. Okay. Do you think the slopes predicting household income in the 2 simple regression equations, predicting household income simply from the wife's education and then from the husband's education separately, the 2 simples, would be the same as in the multiple regression? Do you think they'd be the same as these? Remember, the multiple regression equations are the partial slopes. They only explain the part due that each one of these x's contribute after accounting for the other ones, right? After accounting for the other ones. They're just the partial slopes. So no, they're not going to be the same if they're correlated. If they were 100% correlated, then, like if x1 and x2 were 100% correlated then to each other, then adding, after you added x1 and adding x2 wouldn't help at all, even though separately it would. So, no, they'll both be larger in the simple because they're all positively correlated. No, they'll both be smaller because there are fewer variables. No. It's impossible to know because they're all correlated with each other. Yes, they would still be the same. You know they're not going to be the same because they're correlated. All right? They'll be larger because they're all positively correlated. So when you put them in the simple one, so when you put them in the multiple, the part that's positively correlated will be double counted basically. So it won't count as, when you put it in the multiple, the slope will get smaller because it's a partial slope. It's going to explain the part that's left after you've already subtracted out the part that's correlated with the other variable. Okay? If they were, some were positive and some were negative, you'd know they'd change, but it would be hard to tell how. Okay. The multiple correlation is this. How is that calculated? Now, the first thing to remember is this R is just the multiple correlation, and R is only defined, it's a correlation coefficient, it's only defined between 2 sets of numbers. That's all. R is always defined between 2 sets of numbers. So you have to have 2 sets of numbers. In multiple correlation, the 2 sets of numbers are what? Your predicted y's and your actual y's. That's the 2 sets of numbers. Okay? So R is the correlation between 3 sets of numbers? No. 3 variables. Each of the 100 was predicted. Each of these has a predicted income from the regression equation and an actual income. And R is the correlation between those 2 sets of numbers. Yes. R is only, remember, R is only defined on between 2 sets of numbers. Okay. R is calculated by converting the two variables. You'd have to convert two. You can't do three. This is how you do it, but you can only do two sets of numbers. You can't do three, two z-scores, and then take it. That's how you do it. Okay, so now let's continue. Do the chi-square and f test for the overall regression. So what do we need here? What do we have? Okay, we were told that r is equal to 0.4, right? That's what we were given. We are given that n is 1, 2, 3. This is r, that. Given n is 1, 2, 3. What else do we need? And we need the number of parameters. And what is the number of parameters? 3. That's 1, 2, 3. Okay, now we're set. We can do these. And it's pretty easy. Okay, so r squared, f is going to be r squared, which is 0.6 over 1 minus r squared. And then you're going to multiply it by, let's do this, chi-square is easier. Let's do 0.16 over 0.84, r squared over 1 times n. That's 1, 2, 3, 123. And I got 23.48. Now to do this one, I won't get confused because I know it's going to be close to 123. The ratio is just going to be a little bit less. It's n minus p, so that'll be 120 here. And now I have to p minus 1, so that's 3 minus 1 is 2. Okay? That's what it looks like. And this one, 11.428. See, they look really different because this one's divided by 2. This one didn't affect it much. So now we've got these two. All right, now look at the chi-square table and look at the, okay, at critical value this. We want to look at it, so we have to go look at critical value. And how many degrees of freedom does it have? It has 2, remember, chi-squared is going to have 2 degrees of freedom. It's the same as that. And f, if we looked at the f, it's going to have 2 degrees of freedom in the numerator. These two match up. But then it also has that extra one in the denominator. So that's what it looks like. Okay. So we have to look on this, and they're asking us to look on it with alpha equals 0.01. All right. So looking at the table, 2 degrees of freedom is right here. And alpha equals, this is the same as 0.001. This is the same as 0.01. And this is the same as 0.05. So that's 0.1%. So this is the critical value right there for the chi-square. So that's 13.82. Now, our chi-square is bigger than that by a lot. So that means our p-value is less than 0.1%. It's further out on the tail. So the p-value has to be less than that. It's not between that or greater than that. Does that make sense to everybody? Okay. Now this one, look at the f. Okay, f with 2 and 120, we need the critical value. We need to compare our f to it. All right. So f. So we're looking here at f. See, I don't have 0.001, so we're just going to have to make do with this. Now, 2 degrees of freedom in the numerator and 120 in the denominator. So this right here is the critical value. If we're bigger than that, we know we're more extreme and our p-value is less than this. So let's write that down. So we've got, all right, so the critical value is 4.7865. Our f-stat is bigger than that, more extreme, so our p-value is less than 1%. Does that make sense to everybody? All right, so we've done that. Now let's move on. Still have a bunch to do. All right. Now, suppose you decided to reject the null. You'd conclude what? Remember, at least one of the slopes. So that means either the first slope, the second slope, or both. That's what is significance that would mean. Suppose I did a t-test and a z-test to see if the slope was significant. And I got a p-value just under 5% by one and just over 5% by the other. Which is which? Remember, fatter tails, bigger p-values with the t. So that's the answer. Okay? Now, how are you going to remember the degrees of freedom for the t-test? It's the same as the degrees of, it's this, the same as for the degrees of freedom 2 here. So it's n minus what? You know it's n minus something, and so it's going to be 123 minus 3, 120. So it's n minus p. Same as the f-test degrees of freedom. Okay, if I delete something from the model, now if I add something to the model, r squared goes up. If I add a variable to the model, r squared will go up or stay the same. It can't go down. But here I say delete. So it has to, if I delete something, it has to go down or stay the same. It has to go down. The only way it could stay the same is if it was uncorrelated, but it's correlated. So it has to go down. We lose information, lose prediction. Now, I decide to add a third variable. Since both look like good predictors, I check the correlation matrix and see that this third variable has no correlation with either x variable already in the model oh, wait a minute, I better read, this is complicated. I decide to add a third variable. It's either A or B, the third variable. I check and see that the A one has almost no correlation with either x variable already in the model, and the B one has a correlation of almost 0.95 with the husband's education. Which variable should I add to the full model? You shouldn't add one that's very highly correlated with another one. That's really bad. Multi-correlinearity, it won't make any sense. Putting two variables together that are highly correlated causes problems. It's like the left foot, right foot size of those feet. If you were predicting height, your left foot and your right foot almost do the same thing, and putting them both in the model just gives you screwy results. All right, now let's read this last one. Where are we going? All right, which group has a positive relationship with x and y? This is the only one that's positive. So that's group C. Which scatter plot has an overall positive relationship? Well, that's plot 1. For which plot does there appear to be an interaction? This has a slope going this way. The slopes are different for the two groups. There's an interaction between group membership and your x variable. You'd have to include this x times group membership, so this one. Let's say we're trying to figure out if x causes y. For which one is the causal relation between x and 1 confounded? Well, check the two conditions. They both have different x's. And look, you can see these both point down and this is pointing up. And same here. This one is not the average of these two. They're both confounded. This one should have a positive overall. This should have a negative, but their group, it goes in the overall regression goes in the opposite way. So they're both confounded. All right, let's see which ones we should do now. We don't have that much time. Should I just keep going in order? We only have 5 minutes left. We can do this one. Might as well finish this one. All right. So, what are we going to do here? Here's our n, right? And we have to fill out this table. What are we given? We're given the sum of squares total and the sum of squares between. We know these two have to add up to that. So this is pretty easy. 4209. We're supposed to fill out this table. We have these 4 different averages, and here's our n's. Now, we're testing the null hypothesis that these 4 group means, how much time they spend on the phone talking with their parents are the same in the population, regardless of the ethnicity, okay? I mean, they have nothing to do with ethnicity. So we're trying to do a test to see if any of these are different, or if the null is they're all the same. So now we need our degrees of freedom here. Now the degrees of freedom are n minus 1 total, so that's 182. Now, what's our number of parameters here? It's the number of groups. So our number of parameters equals 4. So the model is P minus 1, so that will be 3. P is G, the number of groups minus 1. And they have to add up here. And this is n minus 1n minus 4. N minus 4, right? All right, now we just do the division. To get to this, we just say that divided by 326 divided by 3 is the mean square. And 4209 divided by that is 23.514. The F ratio is just the ratio of those two. So it's 108 times 67 divided by that. And we get 4.62. Now, how are we going to get the p-value? We have to compare to the critical value, right? Some critical value, we're not sure. Let's look at our table. Remember, what do we have here? Which curve? We have 3 and 179. So let's quickly look at the table, because this might be hard. We look at the table for 3 and 179. 3 and 179. Well, we're much bigger than that. Let's see, how about here? 3 and 179. RF is 4.62. Now let's look at the bigger one. It's going to be somewhere in between here. Since RF is bigger than that one, it's going to be bigger than both of them. So let's compare to that critical value, because it's this, because we were way bigger than the other one. What does the question ask? Let's go back to the question. So we're going to compare to the F star, we'll compare it to that one, 3.949, and that was at 1%, so we can say it's less than 1%. You can't do it exactly, but we know it's less than 1% because that was at alpha equals 1%. All right, now this, the SD plus errors, you just take the square root of that. .85. And then our last thing is r squared. You know how you'll get that? Remember, r squared is just the proportion of the variance of the total variations, and this is sum of squares between the proportion of that due to the model, right? So we did that before. So in this case, it's going to be 326 over 4535. Remember, this is r squared times SST, and this is 1 minus r squared times SST, and they add up. That's equal to SSB. All right, so we got that, and that turns out to be 0.0719. All right, we just have, do you mind if I go a few more minutes just to finish up this up to here? Is that okay? Just another minute Okay, so what is the standard error difference? The standard error of the difference. Remember what that is. You're going to be using this right here. It's the standard this is going to be here. Boy, use this piece of information. I would give it to you elsewhere. I wouldn't, because there's too many continued errors, but look at that. So we check that we got that right. And so you're going to use that. It tells you right here, use that as your pooled estimate. And remember, you multiply times the square root of 1 times the sample size for one group plus the sample size for the other group. So in this case, it's 4.85 times the square root of the two groups we're doing are whites and East Asians. So it's 55 plus 1 over 91. I think, you know what I can do? I can finish the rest of it and post it, okay? So you get to go.